No, mute.
It's been 3 days. It's been 3 days. You people are with us. We are very happy to have you all in this 3-day online training program, Futuristic Research in Disaster Resilience, jointly organized by VVCE and NIDM. I'm Kanmani SS, Assistant Professor of Civil Engineering Department of VVCE, will be the master of ceremony for today's session. Today, in the first session, we have with us Dr. Babu Narayan sir, Professor from NITK Surat, to speak about nature, structure, and future, along with our professors as panelists. To start with, let me invite Professor Chetan Yel, Assistant Professor of Department of Civil Engineering, to welcome the gathering and to introduce Dr. Babu Narayan sir to everyone. Over to you, Chetan sir.
Thank you, Kanmani madam. Good evening. Thanks to each and every one of you for being here with us today. I'm very pleased to welcome everyone present on the occasion of the 5th lecture of online training program on Futuristic Research in Disaster Resilience, being organized by Vidyavardhaka College of Engineering, Mysore, and National Institute of Disaster Management, Minister of Home Affairs, Government of India, New Delhi. First of all, I have the pleasure in welcoming the eminent researcher, a great teacher, and today's speaker, Dr. K.S. Babu Narayanan, for the occasion. Welcome you, sir. So, I also welcome Professor Chandan Ghosh of National Institute of Disaster Management, New Delhi. Welcome you, sir. So, I would like to welcome Dr. S.K. Prasad, Head of the Department of Civil Engineering, VVCE, Mysuru. Welcome you, sir. So, and also I would like to extend my heartily welcome to Dr. H.S. Dayananda, Dean Academic Affairs, and Dr. Umesha P.K., Professor in Department of Civil Engineering. And also I would like to extend my welcome to Professor Kanmani S.S. Raghavendra S.S., the Coordinator of Research Studio. So, also I would like to take this opportunity to welcome all the guests, all my colleagues, and also dear friends and students. Okay, most important for any activity is the participants. I know all of you have been come together in a large number to listen to Dr. K.S. Babu Narayan sir. I wholeheartedly welcome all the participants. And I have the pleasant duty to perform today, that is to introduce Dr. K.S. Babu Narayan sir to all of you. So, Dr. K.S. Babu Narayan is the professor in Department of Civil Engineering at National Institute of Technology, Karnataka, Suratkal, has obtained his BTech from KREC, Mysore University, MTech from IIT Bombay, and PhD from NITK, Suratkal. His areas of research interest are structural analysis and design, RCC, PSC, and steel, structural optimization, math modeling, and unsaturated soil mechanics. Dr. K.S. Babu Narayan has several significant publications in many national, international conferences and international journals such as American Society of Civil Engineers, Journal of Forensic Engineering, Journal of Mechanics, Structural, and Conferences. He is awarded with HUD-CO Excellence Award for the promotion of cost-effective construction technology in 2002. He is a recipient of Young Civil Engineer 2007 Award instituted by the Institute of Engineers India, Outstanding Constructor Award in 2016, ACCE. So also, he is also a GJEC visiting professor, Kumamoto University, Japan. He has guided 7 PhDs and 4 are ongoing. I deem it an honor to present you to the audience for delivering the first lecture of 3rd day of the online program on Futuristic Research in Disaster Resilience. It's over to you, sir. Thank you so much.
So, thank you, Professor Chetan sir. Sir, before I hand over the session to the speaker, I have few things to tell to the dear participants. That is, if you have any queries to ask our speaker, you can post them in the chat box along with your name and location. Those questions will be taken by our panelists after the presentation. And feedback links will be posted in the chat box. Kindly give your valuable feedback. So dear participants, kindly note that the e-certificates will be issued to only those participants who have registered in NIDM portal and on submission of all the feedbacks. Now, without any delay, let me hand over the session to Professor Dr. Babu Narayan, sir. Over to you, sir.
Thank you very much. Shall we?
Yes, sir.
Yeah, please.
Start sharing the screen.
Yes, sir. You can start sharing.
Yeah. A very good afternoon to you all. And I'm extremely happy to be with you all this afternoon. So let me begin it this way. If you go to any huge facility, a big complex, a big institution, a university, the first thing you see there is the signage, you are here, which directs you to different locations and different facilities. Wherever you want to go, you can reach. All right, one university decided to do it in a slightly different way. Why they should not be different? Let us be slightly different in putting this signage, you are here. So very interestingly, the Department of History, the signage was, you were here, because for them everything is past. And if you go to the Department of Linguistic Studies, the signage was, mind your language, for you are here. And if you go to the Department of Logics, the signage is, you are here because you are not anywhere else. And if you go to the Department of Futuristic Studies, the signage is, sure, you will be here. And if you go to the Department of Criminology, they have a question, why you are here? So we all know why we are here. And I thank everybody for the opportunity. It's really an honor to be here. And I'll be making a brief presentation on nature, structure, and future. I've got about 60 odd slides to tell you about nature, structure, and future. Okay, the first of the slides, what you are seeing is a wonderful small book published by the Reader's Digest. It's one of the most popular books, Know Your Body. One of the greatest gifts to us all by nature is our body itself. What a well-organized system. You have the heart, you have the brain, you have the lungs, you have different organs, you have the circulatory system, the respiratory system, the digestive system. You have the skeleton, the skin, the cartilages, the bones, the tissues. So very well organized. That's why they say one of the best, the most well organized system is the human body itself. And a few facts about this organization: the right materials, the right positions, right? And so much can be accomplished by this human body. If you take the heart, the moment anybody is born, it starts ticking. And it does so till one is dropped dead. Right? Almost 6 liters of blood pump every minute. And if you work out at a pressure of about 130 millimeters, that is about 5 inches of mercury, if you work out the power outage, the power output comes to about 2 watts, around 2 watts, with different conditions. An amazing pump it is. And coming to the brain, if you see literature, the memory capacity of the brain is 2.5 million bytes, million GBs. 2.5 million GB is the memory capacity of the brain. We, in fact, are all blessed with a great system that works. It is called the human body. And we should thank nature and God Almighty for that. Right? And what we have done is, we have done to mimic ourselves in what we call as the robots. What you are seeing is one of the most sophisticated robots, that is Asimo. Asimo can play games. Asimo can meet and greet dignitaries. Asimo can do lot many things. These robots are mimicking ourselves, and today we have robots that do very difficult tasks where we cannot venture and do it in very difficult situation. And we are using robots even in surgery. And during this pandemic, you must have definitely read or seen the TV screens, many super specialty hospitals where COVID patients were managed, they were using the robots. It makes much sense, and it is more economical too. One example of how we try to emulate nature. Well, that brings me to the bird's nest. Birds know how intricately to construct their nests in different denominations and different configurations. The bird nest comes. They know what the right material, what is the right flexibility, what is the right stiffness. Most safe and sturdy nests they do construct. We are taking cue from the bird's nest to do mega structures. We are also building huge facilities like stadium, taking cue from how birds configure their nests. Here are some pictures for you to see how huge facilities like stadiums and huge column-free areas can be configured after the bird's nest. And shell forms. We all know the shells derive their strength because of their form. A folded plate is stronger than a flat plate. Anything that is curved is stronger than anything that is flat. A singly curved shell is stronger than a plate. A doubly curved shell is more so. And if you have a shell like a saddle surface, this curvature positive in one direction, negative in the other, it is even more stronger. We decide whether it is developable, whether anticlastic or thicklastic, based on what we call as the Gauss curvature. And the shells use very minimal amount of material to get us this strong form. And again, the desired mode of failure. You have two pictures or two images here, one on the left top and the right down, and a chick coming out after the egg has got hatched. It is very strong in compression, but at the same time very weak in tension. If it were equally strong in tension also, the chick, the small baby cannot come out. The desired mode of failure, in what it should be strong and in what it should not be. If we are taking cue and we are using shell forms and folded plates in many of our structure, and also we are talking about what do we call as performance-based design. What is the desired performance level? If at all there is failure, in what mode it should fail, and so on and so forth. This is what we have understood from nature. And here are a few examples for you on huge shell structures. What you are seeing on the right is the very famous Inamori Auditorium. This is the form of a huge sphere. And this is another example of functional flexibility. These days, we are talking about more of transience than permanence. If one thing can serve many purposes, many in one, all in one, and so on and so forth. Even in terms of vehicles, we have MUVs, multi-utility vehicle. Can be used as an estate wagon, it can be used as a sedan, it can be used as a sports car, and so on and so forth. Even in terms of structure and infrastructure and facilities, we are thinking of multifunctional, multi-objective. Right, here is one example where everything is deployable. This can function as an indoor stadium and an outdoor stadium and for different kinds of games and ball game. This is from Japan. This is the plan configuration. This is the soccer field. There's another picture showing you the seating arrangements. And this is how the roof is organized. The roof is deployable. Roof can be slid and you can make it an outdoor stadium. Right? Very good. Yes. The whole roof can be slid and the whole picture becomes like an outdoor stadium. And the seating arrangement can also be configured as you want for different ball game. This is how it looks from inside if the roof is closed as an indoor stadium. And this small animation which tells you how the system is managed. The lawns are rolled up. The seating arrangement shifts. The whole field moves, rotates. The seating system changes. And they have another mode. Such mobile systems. We are even talking about deployable structures, multifunctional, which can serve many purposes at the same time. One feature for many use. Very insignificant and small objects like pins, paper clips, pencils, beverage cans can teach us a lot. The only thing is we should have the inquiring mind. Right? We look at an object and we should try to understand why it is so, why the design is so, why it has been devised so, and so on and so forth. These insignificant everyday objects can teach us a lot about structures, our requirements. Pins to paper clips itself is a very interesting development. It's not simply easy to make a paper clip. What should be the material of the clip? What should be its springiness? How rigid it should be? How flexible? If it is too rigid, it cannot be used as a clip at all. If it is too flexible, also it cannot be. It should have the right stiffness and the right softness. That is how it works. And whenever you are thinking of doing something new, the new has to displace the old. And that can happen only when there is a distinct and clear advantage. You have something and you want to do something else. There has to, unless there is a very clear and distinct advantage, you cannot displace the old. So that should be very clear with us as to, is there anything wrong with what is existing? Do we really need to enhance its capabilities? What are the limitations? What are the drawbacks? And is there any chance to make it perform better? And so on and so forth. We should remove the objections to the old. Then only it can be accepted. And many times things can be long lasting owing to familiarity. People are happy because they have been using it from long and it is serving their purpose and they are satisfied with the performance and so on and so forth. So all these things should be remembered by those who are into innovation or into research. What is wrong with whatever already we have? Are there any limitations? Can we enhance the performance? And if we can, what needs to be done? What objections or what disadvantages or what limitations need to be removed? That should be a clear understanding. And from pins to paper clips is, I told you a very interesting story. Earlier we were using the pin. We had difficulty in threading. The pins leave holes in the papers. The pins rust. And if you have seen files pinned and kept, it bulks up the file. It tears other papers. It pricks the fingers. You may even get injured. The clip removed many of these shortcomings. These shortcomings like difficulty in threading or the puncturing the paper, rusting, bulking of the file, tearing other documents was all removed by this small object, very tiny object like the paper clip. And if you go to the net, you will find this. the largest number of patents filed is for the design of the paperclip. So that is what I meant by insignificant and very tiny small objects of everyday use can teach us a lot. Okay, this again is a very interesting development. Many of the youngsters may not be knowing, at least elders know. Earlier, inks were stored in reservoirs and quills were used to write. You can see the reservoir and the quill, right? From there, we advanced to the fountain pen. The problem with the quill and the reservoir for the ink is you should have the skill to immerse the quill, to take it out, write with the quill, and take it back. It should neither be more nor less. If it is too less, the ink you have picked is too less, you can't write. If you have picked too much, you will, that is more or less, you will be making a mess, and sometimes a royal mess. And on the left bottom corner, you see the mess created by spilled over ink. And from there, we advance to the fountain pen. No more quill and reservoir. The pen itself has the reservoir and the nib works as the quill. And from there, we advance to the ballpoint pen and to the refill or the disposable or expendable cartridges. This is how you have difficulty with what is existing, and you have advantage over what is suggested as new or an innovative method. That is how it advances. Okay, so that brings me again back to pencil. All right, pencil may be a very insignificant object, but it can teach us a lot. On the right hand top corner, you have the image of Professor Henry Petrosky. Professor Henry Petrosky, professor at Duke, is known very popularly as the pencil professor. All right, he is a prolific writer, and I am his fan. He writes a lot on different aspects of engineering, and one of his work is the pencil. And there he writes the history of pencil. The broken off pencil points can teach us a lot. And before I tell you about the broken off pencil points, and many times it has been declined also, this joke about the pencil. During the Cold War times, the Americans and the Russians had the space war. Who will put the first man on moon? Russians called the spacefarers cosmonauts. Americans called them astronauts. Russians had their Sputnik. Americans had their Apollos. And the spacefarers, these cosmonauts and astronauts, go to the space. They acquire a lot of data. They perform a lot of experiments. And they come back and they give the feedback. On one such instance, the American astronauts, their feedback was, pens do not write in zero gravity. So this was taken up as a huge research project, and we should get a pen that writes in zero gravity. And today we have a pen that writes in zero gravity. Of course, it is not because of NASA's or other expenditure, or the government expenditure, due to a private entrepreneur. We have Fisher zero G pen. Anyway, so this was taken up as research and it was given up. And when the Russians came to know about this research, they said, in zero gravity, we use pencils. Pencils work in zero gravity. Right? Pencil is a wonderful object to write. We all learn writing first with pencil, and we use erasers too. We can erase all the errors, and it's very easy to re-document whatever we wanted to. So it's broken off pencil points again can teach us a lot. If you have always anytime observed the broken off pencil point, it has a characteristic way of feeling. It will not feel exactly at the surface, little in, at an angle, and so on and so forth. This became a very interesting feature to be studied, and people started modeling the broken off pencil point as a simple cantilever beam. And research went on to sophisticated finite element analysis model. And this exercise led to our better understanding of solid and fracture mechanics of brittle material. Right? We could understand better the behavior of brittle materials because of our interest in the broken off pencil points. Many fundamental assumptions were revisited, we reinterpreted, we redefined, refined, we scrutinized the studies. That is what I meant by even an insignificant and small object can give us great insight to structural materials and behavior. Okay. Beverage can teach us a lot. The fundamental principles that go into the making of a beverage can is the same as that of a pressure vessel or a nuclear reactor or a containment for a nuclear reactor. Principles fundamental are the same. So what should be the wall thickness, or what should be the roof configuration, what should be the floor, and so on and so forth. But when it comes to a beverage can, you have other issues too. How easily it should be opened. It should not be too easy, it should not be too difficult either. And when you try to open the can, the whole lid should come off. Should not come off. There has to be a desired mode of failure. What shall be the material? If it is a material like steel, if it rusts, even after opening and when you drink the beverage, you may injure your lips, and so on and so forth. All these are issues. And if you closely observe a beer can or a beverage can, you will see the bottom is like a dome. Under the pressure of what is contained inside, if you make it flat, it bulges the other way, you cannot place it on the table. So insignificant and simple objects, everyday objects like this can give us a lot of insight to how we meddle with structures and features. Yes, of course, we learn to fly seeing the birds. Seeing the birds, we always wanted to fly, and we have wonderful flying machines these days. Birds inspired us to fly, and whole of flight dynamics is at a different level altogether today. And we understood wind engineering and computational fluid dynamics much better because of our interest to fly. Today we have very sophisticated wind tunnel from where we can acquire tremendous exhaustive amount of data to understand the flow patterns of flow visualization and the wind effects. We make such studies and we build machines like formula cars, we build aircrafts, and also we build wonderful structures that can accommodate the wind loads. And here is one example of a wind tunnel test model where there is a turntable to check the performance of the battery of buildings for pedestrian level wind effects or others by just turning the table. And the image below shows an aircraft model subjected to wind tunnel testing. Can acquire tremendous amount of data, and later we can use this data to validate our many theories and hypotheses. And that brings me to this interesting thing where the Shinkansen's nose has been inspired by a bird, that is a kingfisher. Japanese are very proud of their bullet trains, or Shinkansen. They run at speeds exceeding 220 kilometers per hour. There are different denominations, 220, 330, and for the Olympics, Japanese wanted to run bullet trains exceeding speeds of 100 kilometers per hour. And Japan is a group of islands. They have just about 25% of the space available to them habitable. And many of these tracks are through tunnels. And when you do a tunnel, to minimize on the materials and also the time, money, and efforts, critical sections, very minimal clearances will be left and the tunnels are made. And when the Shinkansen's speed had to be enhanced, they had a problem. A high-speed train moving in a tunnel with a very minimal clearance is almost like a piston moving inside a cylinder. That too, these high speeds, and the train moves, the air gets tremendously compressed, and you have very brute forces acting on the carriage itself, and also on the frontage. There will be a lot of vibrations, and there will be sonic boom too. They were meddling with many of the features, and one of the team members was a bird watcher. He was inspired by the kingfisher. And on the left side, you have the image of the kingfisher bird. This bird dives to water to catch its prey, that is a fish. And when it does so, it does with great speed. It will not injure itself. It will not create even a splash, and he catches the prey without much fuss. So this engineer felt, why should not we model the nose of the Shinkansen after the beak of the kingfisher? The kingfisher beak has a feature which is almost a rotational paraboloid. They adopted that, and whatever problem they had got solved. So this is an example where nature has inspired our designs. The kingfisher's beak is the inspiration for the nose of bullet train of the Shinkansen. And this in a lighter vein, have put what you are seeing is the bumblebee. The body of the bumblebee, the features, the tiny wings, none of them are fit for flight dynamics. In fact, strictly according to computational flight dynamics, bumblebee should not fly. And jokingly, people say, in spite of that bad design, aerodynamic design, bumblebee flies because bumblebee does not know flight dynamics or computational fluid dynamics. Why bumblebee flies is he flaps the wings very fast. A very high frequency at which the wings are flapped enables the bumblebee to fly. So here we have the caterpillar. Another interesting design by nature. This worm has a cylindrical body. Just imagine this worm with two legs in the front and two in the rear. If it had just two in the front and two in the rear, the body would sag like a simply supported beam, and the belly would touch the ground. And to accommodate the sag, the only way is you increase the height of the legs or the limbs. If you do that, you need more material because anything that is very slender under compression will buckle and fail. So instead of that, nature's way of solving the problem is you have many legs that are short and stocky. So that is what it makes the caterpillar move in any terrain. And we have taken cue from the design of this caterpillar, this worm. We also design all terrain vehicles. You can see one working in the image below. And the name of the firm itself is Caterpillar. We do heavy engineering equipment that move in all terrains. And the inspiration is this worm, Caterpillar. And that brings me to the spider and its nest. Very intricate detailing. You see the nodes, you see the elements organized. definitely a tension structure. The spider keeps moving all over the net. It does not get caught. The prey gets caught in the web. Very interesting. What kind of material it is? What is the denomination or the area of the strands? How it knows how many nodes should be there and how the whole net should be organized is all very interesting, and it is being studied. And there are a lot many interesting papers on the spider net or the cobweb. You will find very interesting, get to read very interesting materials, and many of the spider nets or the cobwebs can sustain hurricane. And in structural mechanics and also in biomechanics, people are making studies on the spider net, the features, the material, the configuration, how it derives its stiffness and softness, and so on and so forth. And we are also inspired, and we do huge structures of this kind, column free areas. We are seeing on top is a hyper. Here again another tension structure, making use of cables. And tension structures demand very minimal amount of materials to. There are other issues like aerodynamic stability, flutter, and so on and so forth, which can be managed. But then we are inspired by the spider net or the cobweb for these kind of structures. Yeah. That brings me to this man, Santiago Calatrava. You can see a bridge, a cable-stayed bridge. You know, as the civil engineers and in civil engineering parlance, one who can design a bridge can design almost anything. Whatever we study in civil engineering, right from the beginning to the end, if everything has to be put in one structure, that is the bridge and the bridge alone, we study engineering mechanics, we study structural mechanics, we study fluid mechanics, we study soil mechanics, we study influence lines and moving loads, we study dynamics, everything we study. If one structure that gets into the making of it is the bridge. And here you are seeing a fantastic bridge conceived and designed by Santiago Calatrava. Santiago Calatrava is an architect and he is a structural engineer. He holds a PhD in structural engineering. He is one of the finest contemporary architect engineer in the world. We all are used to see and know and understand about these cable-stayed bridges. And we are all very familiar with the vertical pylons and symmetrical cable arrangement on either side, whether it is the harp type or the fan type. But here you have an unusual cable-stayed bridge where the pylon is inclined. All right. So Santiago is known for such unconventional and not so traditional designs. So his explanation is, if you take the cables, the force is tension. If the pylon were to be vertical, under the tension of the cable, the pylon will bend and will have a tendency to move towards the right. Since he wants to avoid backstays, he proposes an inclined pylon. The pylon inclined at almost about, it is 58 degrees in fact, say about 60 degrees to the horizon. And now the weight of the pylon itself will counter this tendency. And he calls such arrangements as optimal structure. And his argument is for structures that are sculptures. And he has built many, and one such inspiring bridge, this is in Barcelona. It is like a harp. Harp is a musical instrument. In Western music, we call it as the harp. And in Indian classical music, we call it as the santoor. Pandit Shivakumar Sharma plays the santoor. This bridge is almost like placing a santoor across a river. And this is Santiago Calatrava's conceptualization. And he is right. And he has understood nature the best. All right? So this is what I am saying now is very important. Nature by nature is stingy. Nature by nature is stingy, and nature by nature is lazy. That's why we have law of conservation of mass, law of conservation of energy, law of conservation of momentum, the minimum energy theorem, and the theorem of least work. All this is because of how nature works. That's why I told nature by nature is lazy, nature by nature is stingy. It does not expend. Nature follows the path of least resistance. Right? This is a great cue to us all from nature. Nature believes in minimum effort, maximum effect. So this is one example of an optimal structure by the most famous architect engineer Santiago Calatrava. I have another view of the same bridge for you here. And the next is the night view illuminated. It is like placing a santoor across a river. So that brings me to this great man. You're seeing Professor T.Y. Lin. Professor T.Y. Lin has done a lot for standardization and popularizing pre-stressed concrete. The very technique of load balancing in pre-stressed concrete was suggested by him. And what you are seeing on the right is conceptualization of a bridge for a gorge in America by Professor T.Y. Lin. This has not been built, but Americans want to build this one or the other day. You have a curved pre-stressed concrete superstructure for the deck, and it derives support from cables radiating and anchored to the mountain side on the sides. This is called the Rakke-Cheki bridge. Makes very interesting reading. You will find articles about this in the net. That is the man who suggested the concept of load balancing in pre-stressed concrete. He has done a lot for popularizing and standardizing pre-stressed concrete construction. Professor T.Y. Lin's Rakke-Cheki bridge, inspired by integrity or tension structures in nature. That's another view of the bridge conceived. A curved bridge suspended from cables that get anchored to the mountainside. Well, we have many suspension bridges too. Here is one image of a suspension bridge. What is very interesting is you can see two men on top of the sheath of the cable who have gone up for maintenance. And when you compare the size of these men who have gone up for maintenance with the size of the cable, then it will give you an idea of what should be the size of the bridge itself. In terms of spans in suspension bridges, we have started talking about in kilometers. And the longest suspension bridge in the world is the Akashi Kaikou bridge of Japan. The central span itself is 1,991 meters. It is almost 2 kilometers. It is the central span of this bridge, the Akashi Kaikou bridge. And everyone will wonder why it should be 1,991 meters. In fact, it was planned and designed with the central span as 1,990 meters. The most famous or the infamous Kobe earthquake broke its own record by extending it by a meter. It was planned and designed for 1990. Because of the shifting of the supports, the bridge broke its own record and the span became 1991. We're talking in terms of kilometers as spans in suspension bridges, inspired by the tensegrity structures or the webs, spider nets, etc. in nature. This is a small example of a tensegrity structure. These days, many such models or images do rounds in social media. You must have also received many of them in your WhatsApp. This is a small model that we all did for a student project at St. Joseph Engineering College, a tensegrity structure where we have tension and compression fields. Here we have used concrete for the compression elements and steel cables and rods for the tension elements. And the concrete that has gone into the making of this model is concrete impregnated with self-sealing and self-healing bacteria, which can enhance the durability of the structure. A small example of a tensegrity structure, a student model done at one of my students is a professor there, Bhaskar Malwa. His batch wanted to do something different, and I participated, giving them some ideas about how this model can be done. They could get little assistance from DST also. Right? So, tensegrity structure. Okay, that brings me to something on ants. You will never see a traffic jam when ants move, and people are studying the movement of ants to manage traffic better. And yes, the first of the rules in ant traffic is no overtaking, according to their study. All right, they are trying to understand and they are trying to emulate the rules followed by ants moving in single file to avoid traffic jams in metros and megacities. People are doing a lot in terms of what best can be done in engineering, science, and technology by observing what we get to see as observable nature. Yeah, this is again another interesting thing which you will find in the net. Mysore has the Central Food Technology Research, CFTRI, Central Food Technology Research Institute. One of the scientists in a backyard experiment, he created colored ants. Right? You feed ants colored solutions, sugar solutions, they get colored. Not only you get to get a lot of data about the ant movements, you can even trace and track them. Right? An interesting slide. Creation of colored ants by feeding sugar solutions colored. You can keep tracking the movement and tracing the movement of ants to understand how they behave in a better way. Yes. That brings me to ultra high rise structure. We have many structural systems for tall buildings. At the height of multi-storied building increases, gravity is not a great issue. The problem is with lateral loads, and lot many systems have been configured to take care of lateral load effects. And one such is what we call as the tube-in-tube concept. And all the super tall buildings in the world, they owe a lot to this great man called Fazlur Rahman Khan. It was Fazlur Rahman Khan who realized such structural form. And we should be very happy because Fazlur Rahman Khan belonged to the undivided India. Fazlur Rahman Khan is a Bangladeshi. He studied at College of Engineering, Bengal. Right? He suggested these structural systems for super tall building. And we are using such systems almost all And he was a part of Skidmore, Owings and Merrill, who are the designers for even the tallest building in the world, that is Burj Khalifa. He first suggested such structural forms. And yes, what you are seeing is the image of World Trade Centers, Twin Towers, during construction. It took many years for design and many years for constructing, almost about 7. Right? They were built with the tube in tube concept for the structural form. But then it took just 70 minutes for Osama bin Laden and his men to bring the towers down. Osama bin Laden is also a civil engineer. And many people say this feat as one feat where engineered failure was adopted. Right? And even in this failure, we learned a lot of lessons. When the towers came down, they came vertically down. They did not fall sideways. The twin towers were 442 meters tall. When I say 442 meters, it's half a kilometer up. The towers did not fall sideways. They came vertically down because of this tube in tube configuration. What happened? And we learned a lot of lessons from this failure too. And yes, again, we are getting cues from nature as to what we should do with ultra high rise buildings. What you are seeing on the right is the image of the Sears Towers. On the left, you have bamboo. Bamboo is a variety of grass. And bamboo grows to heights exceeding 90 meters. When I say 90 meters, the height of a 30-storied building. All right. And if you see the structure of the bamboo, bamboo is hollow, like a hollow tube. And at regular intervals, you have the nodes and the diagrams. And you know from your knowledge of strength of materials and mechanics, anything that is hollow makes sense as far as the bending stresses are considered. Most of the material should go to the extreme. So nature knows this. And also, anything that is very thin buckles and fails unless its effective length is controlled. So the stresses due to the weight of the bamboo itself and due to wind is the largest at the bottom. So the nodes are spaced closer at the bottom. They are not, the spacing of the nodes is not the same. It varies. It's closer at the bottom and varies as you go up. And people are making studies on, and also for your information, many varieties of bamboo have tensile strength exceeding that of steel. Tensile strength of bamboo exceeds steel. It's a wonderful material. And we are studying bamboo to configure our outriggers in multi-storied building. At what locations we should have the outriggers, which is the most optimal location for that, how we should configure, and so on and so forth. These are some details about some equations on internode length, internode diameter, what should be the wall thickness, and very interesting features you can see. Wherever the stresses can get concentrated, there are fillets too. You can distinctly see the different spacing of the nodes as the height increases. And we are using such observations in designing super tall buildings. Well, what you are seeing is the plan of Burj Khalifa, the tallest building in the world now. Right? This building has the buttressed core as the lateral load resisting system. And the very plan configuration has been inspired by, according to the architects. Again, this building has been designed by SOM, Skidmore, Owings and Merrill. Adrian Smith is the architect and William Becker is the designer. They say they have been inspired by the desert flower, spider lily, to arrive at the configuration for this building. The inspiration is the desert flower. And if you see the tower, it spirals. Many of you, if you have seen a tall and slender chimney, at the top of the chimney, we put the strakes, the spiral strakes, to make it behave better due to wind-induced vibrations, to suppress vortex shedding and wind-induced oscillations. We use the spiral strakes in very slender chimneys. Here, the building itself has the spiral configuration. And in one of the interviews, the designer Bill Becker says, by the configuration of this building, they have confused wind. Wind does not know what to do with this building. So, more than trying to resist, many times in design, what makes sense is to accommodate. How best we can be accommodative rather than in trying to resist. It is as simple as you hit a wall, who gets hurt? You get hurt. Because action and reaction are equal and opposite. You hit the wall harder, you get a fracture. So we should avoid, instead of trying to resist something, if we try to accommodate things, we have a better chance to stand. Yes, this is again another interesting concept. We are using a lot of diagrids as elements in facades, which perform as structural skins too. Against, they give us facility to resist lateral loads, the lateral load resisting system. It's called a diagrid. And people are trying to extend the concept. If you use hollow structural elements for the diagrid, it is being contemplated. You can circulate hot water during winter and cold water during summer to keep the environment at the required temperature. So almost like your shell tube exchanger or radiator. But they want to extend the concept to other possibilities. Otherwise, it performs as a lateral load resisting system. It can be multi-objective. Now, if you circulate hot water or cold water, depending upon the season, it can perform as the HVAC system. And the concept gets extended. People are talking about if there is fluid inside, the sloshing of the fluid inside can give us auxiliary damping. It can enhance the damping characteristics of the structure. It can be advantageous in quake resistance. And people are even suggesting if you use photorheological or magnetorheological fluid, and if its viscosity can be controlled, can we make it a building controlled by both having control over damping and also over stiffness, active variable stiffness. Can we think of doing that? People are contemplating. The imagination only is the limit for innovation. Yes, this is again very interesting. All of us will have played classroom ball games or classroom cricket by making paper balls. If you take a paper and start crunching it, wrapping it, and make it a ball, the more you try to crunch it, the more difficult it becomes. Because what was a sheet earlier, flat sheet, becomes a folded plate, and a folded plate is stronger than a flat plate because of the creases, because of the ridges and valleys. It derives strength. And people are studying the crumpled paper to get some cues as to why it behaves so, and how the creases form, how the energy gets stored, how it gets dissipated. And they are even contemplating such studies can throw some light on the study of Earth's crust, which will make us well equipped in predicting quakes. Yes, and all of you know anything that is hard and strong is dense, and even we are told one easiest way to judge the quality of brick is take two bricks, bang them against each other. If you get a ringing sound, it is good. If you get a hollow sound, it is not so good. It is bad, rather. So noise as voice can be a non-destructive evaluation tool. So whenever you do failure forensic investigations, also you are called to take course, you are called to drill, and so on and so forth. There will be a resistance to drilling and coring operation, and based on the quality of what is being drilled or cored, there will be resistance and noise levels too. So we in our institute tried to correlate these, and we have published a few papers too. How noise as voice of what is happening can be a tool for NDE evaluation, can help us in understanding what is the residual strength after damage. Yes, we are building long span structures and large span spatial structures too. And also, this is the most happening field these days. What do we call as structural health monitoring? We visit doctors, we visit healthcare facilities to get ourselves checked and assessed. And this we are talking even in terms of structures. We have health monitoring systems. We are putting data acquisition systems to acquire data on the performance level and to check whether we are getting the desired performance levels. Is there anything wrong? Is anything needs to be done? And so on and so forth. And many times we are doing in a few instances real-time monitoring. Right now, what is happening, we will get the data and some action needs to be initiated that can also be done. Yes. So having said all this, what the future holds for us. Many people have already started talking about future infrastructure shall have integrated centers like our nervous system with processors and algorithms like our brain, and with actuators like our muscular system. And we'll have very smart structures which behave in the way we desire, the performance-based design, desired mode of failure, whatsoever. In the future, we are trying to mimic biological systems in providing smart structures in future. So this was what I wanted to convey to you in nature, structure, and future. Thank you so much for your patience listening. And I thank the organizers, most of my friend, very good friend, S.K. Prasad, Professor S.K. Prasad, for the honor and the opportunity to share the time with you. And to all of you, have a great day, have a great weekend, and have great times ahead. May God bless us all. Thank you very much.
Thank you, sir. Thank you, sir. That was indeed really an informative and inspirational session, sir. And the design of structures derived from nature, from eggshell to great structures, broken pencil to finite element analysis, beverage cans to pre-stressing concepts, birds to flight dynamics. Wow, I should say many more. We all enjoyed a lot, sir. I got to know that nature knows everything and nature is the best teacher for all civil engineers. Thank you so much for that. Before moving ahead, just a gentle reminder to dear participants, kindly post your questions in the chat box and give your valuable feedback provided in the chat box. Now today, in this session, we have panelists, Dr. Chandan Ghosh sir from NIDM, Dr. S.K. Prasad sir and Dr. Umesha sir from VVCE. I request the professors to handle the question and answer session. Over to you, sir.
Thank you. Thank you. Thank you, Professor Kanmani. Yeah, Professor Babu Narayan As usual, you are fabulous. I really enjoyed listening to you. And,
Thank you.
you really taught us a lot. So I was just wondering how your lecture can be compared with the present theme, but it was so much fitting to that. Uh, the way you expressed everything, as was already put by Professor Kanmani. So you compared nature with engineering, and you said we can learn a lot from nature, and then you took us to some disaster managements. You talked about wind analysis for tall structures. You said, how spider net or spider web, compares with the kind of work which we need to do. And then you talked about the failure of Akashi Kaikou bridge. Not failure, I'm sorry. In fact, the strength of Akashi Kaikou bridge against the Kobe earthquake, where, it expanded by 1 meter more. Okay. And then you talked about WTC collapse and how it was made, very resilient. You said that, the failure was in such a way that it did not disturb the neighboring structures. So it was tube in tube. So lot of things about disaster resilience we could learn from your work. We don't have too much time. I quickly call Professor Chandan to speak a little, and then we have to close this session in about 10 minutes time. There are a few questions. In fact, I was wondering uh, till 2 minutes back there were no questions. In fact, there was only one question. Okay,
Okay,
that
sir.
clearly shows people were also confused. Really, your presentation was so lucid, so good. There was no way we could ask questions. So anyway, there are a few questions. We'll attend to that. Professor Chandan, can you please
Oh,
give your views?
yeah, it is really mesmerizing. Till yesterday, 4 lectures were there, and we were showing that in nature is so complex. Where Professor Babu Narayan started with the human body, it is so complex. And only a few days back, IIT Bombay and Tata Memorial Hospital made an attempt, first attempt in India, about the gene therapy. We know stem cell and many things, and new drugs are coming up, new things are happening. But till yesterday, we are presenting something that maybe nature is much more intelligent and much more, I would say, complex as well as simple. But through this your emulation of the nature and then attempting it much beyond the nature to the music and to the biological aspect of the thing, which your last slide that you are saying. So that is really fantastic, and I think our we are all along with us. We didn't have any question coming in mind because your flow of each and every 60 slides you said in the beginning, they are so systematically arranged
Yeah.
that it is something like that when a guru or a teacher teaches something, and we are all students, and we are just listening to that, and your flow was such a lucid manner is that there is no scope for even any question because it is everything getting filled up in ourselves.
Yeah,
So
but anyway,
not just
there are a couple
question.
of questions, Professor Chandan. Let me just
Yeah, please.
bring in those. But before that, Professor Umesh, would you like to say anything quickly?
Nothing extra, sir. Actually, the design of structures is comparing the nature. That is very important. Every nature is
Exactly.
having for our structural design. I think that's what he has
Okay.
clearly told. So that is very important. I think you should see nature and have to design in future also. That's what I want to tell. Okay, thank you.
Exactly. So let us see, some comments from Professor, Professor Vijayendra of BIT Bangalore. He says, ironically, in our way to mimicking the nature, we are detrimental to it. So he wants your comments.
No, my comment would be, even many times you must have seen when there is a singing competition, if the judge is S.P. Balasubramaniam, and if somebody sings his song exactly the way Balasubramaniam sings, after the competition, even if that fellow wins the prize, Balasubramaniam tells him, it is all right, you mimic me, but you can do better. You should do better. Mimicking is not simply copying. By mimicry, what do we mean? When you take the cue, you take what is best, and you can even enhance it.
Okay. Let me, I understand what you say. Let me just talk about a few appreciations. SKR says that, Babu Narayan sir's session will be always superb and knowledgeful. Unfortunately, today I couldn't attend full session, but still, because of vaccination, but still I'm happy. Susanta Datta says, excellent presentation. A presentation showing the comparison of present structures with nature intelligence. And then, Srinivasan Ramchandran says, nature is the best teacher indeed. Pi and Phi are the best examples. RD says, awesome session by Professor par excellence. This session has been a jewel of the crown of the whole training. So that is, and Rahul again says, good session. Let me come to one question again. Please also share some knowledge on space frame structures, which is in very much use in the current world. You want to say something, Professor Babu Narayan?
What was the question again?
He wants you to
What was the
say
question?
something about space frame structure.
So, one of the exhibits or the slides was the bird nest is a space frame. It is a space
Correct.
structure. Shell is a space structure.
Correct.
We discussed a lot about everything. In fact, everything is space. The two-dimensional idealization is only for us to make calculations easy. Everything is three-dimensional.
Very true, sir. Let me take another question. Sir, as you have given an example of pen, can we use refills of pens in making concrete blocks? I didn't understand. Which will improve compressive strength, just like fibers. Maybe. Any comment on this?
No, the inclusion of fibers need not necessarily improve the compression strength. That should be the first understanding. And people these days have a notion that anything is treated as a waste or it is of no help elsewhere can be put to concrete and something can be done. It is not that way. It does not work that fiber may improve the tensile strength. Definitely, tensile strength and the characteristics, but not necessarily compression at all. And kind of fibers, the aspect ratio, unless some study and some characterization is done, something cannot simply be put to concrete and we cannot expect it to perform better. That is my view.
Right, sir. Shabarish from Hubli says, this explanation of biomimic in structures is excellent. Are there any examples of such structures in India, sir?
Like,
yeah, whatever,
Like
you showed about, mimicking the human things, with respect to nature. I mean, with respect to construction, biomimicking. So there are many structures which you showed, even WTC you showed.
yeah,
Okay. Are there structures wherein we have mimicked nature in India?
many of our temple architecture is inspired by nature. Many of the temples.
Okay.
Many of the temples are inspired by nature.
So, Professor Chandan, you would like to make any other comment?
I want to just one query is that, like in comparison to bamboo, say where it can go even as big as long as 90 meter. Is there any equivalent civil engineering material like hollow pipe or anything where 90 meter L by D ratio for our L by D here, maximum D maybe for a bamboo is 20 centimeter. So 90 divided by 20 centimeter, it becomes 450. Is there any structure in our civil engineering system where we design some member with 450 as L by D ratio?
No.
Whereas bamboo stands and it takes all air and everything. Is there any equivalent civil engineering material?
See, the difference here is that we should understand. Let us say I have a pipe. Unless I have the diaphragm, will have a mode of failure called the local. Local failure and global failure. See, I have a pipe. I have a pipe and I compress it. The whole pipe can fail as one element, that is global. Or the thin wall itself can fail. That is called local, right? So bamboo, what it does is to avoid local failure, it keeps on doing this nodes and diaphragms.
Nodes.
Otherwise, the wall itself will fail. And where the stresses are high, the nodes are closer. And it is fibrous also. That's why I said it is very strong in tension, and some varieties of bamboo are stronger than steel itself.
But have we taken clue from there?
Equivalent like that, even with the nut. Even with the nut, I think we cannot make even FE 650 or whatever steel is there with 20 centimeter diameter. And we cannot make a 20 centimeter diameter, 90 meter high with any of the steel material that we have manufactured ever stand on its own. 90 meter.
No, again the problem there is the unit weight. Unit weight of bamboo is very less. Unit weight of steel is very high.
Okay.
One great comparison is in terms of strength to weight ratio. A material may be stronger, but if it is heavier also, it is of no use. An ideal structural material should have very high strength and very low weight. That's why we spend a lot on what we call a structural lightweight concrete.
Anyway, Professor Babu Narayan, I think
high strength to weight ratio.
Thank you very much. Otherwise, Professor Kanmani would be in a tense mood because we'll have to close now. I really felt,
thank you very much.
You were very motivating. Your lecture was so stimulus. I'm very sure many of us will be in a position to think about, taking clues from nature. I sincerely thank you from my side. But then, I'll have to hand over the session to the MC. Over to Professor Kanmani.
Thank you, sir. Thanks a lot, sir. It was really indeed a very interactive session, sir. Sir, I should tell that it was very, very interesting, very interactive, and we learned a lot. Few days back, Dr. S.K. Prasad sir told me while doing some research, he said, search the solution from nature. I didn't understand that concept then. Now I got to know from Babu Narayan sir's session that how to get the solutions from nature. Thanks for that. Now I request Professor Abhilash sir to propose vote of thanks.
Thank you, Kanmani madam. Good evening, everyone. As we come to the end of the day of the 5th lecture on the online training program on futuristic realistic in a disaster resilience, it's my privilege to propose the vote of thanks. On behalf of the Department of Civil, Vidyavardhaka College of Engineering, Mysuru, and National Institute of Disaster Management, Ministry of Home Affairs, Government of India, New Delhi. I convey my sincere thanks to Speaker Dr. K.S. Babu Narayan of NITK Surathkal for sharing his knowledge and experience. Thank you, sir. Further, I wish to thank all the participants for your active participation in this session. I also wish to convey sincere thanks to technical team, faculty, and staff of Department of Civil Engineering and NIDM. Finally, thanks to all concerned, and we look forward to seeing you all in the next session. Thank you all.
Thank you, Professor Abhilash, sir. Now we are closing this session 1 of day 3. I request all the participants to join us in our next session on R&D in Earthquake Disaster Mitigation by Dr. CVR Murthy of IIT Madras through the link provided in the chat box as well as in the description below now at 5 p.m. See you all again. Thank you.